Hello, everyone. My name is Tianxiang. I'm from the University of California, Los Angeles. And today I'm going to present our work called Supporting Delay-Tolerant Networking, a comparative study of epidemic routing and NDN. I would also like to thank my colleague, Zhao Ning, and my advisor, Lisha, for helping out with this work. So as we know, there has been a growing demand for delay-tolerant communications due to the growth in vehicular networking and satellite communications. So this drives for a need of efficient and secure communication, even under intermittent connectivity and a lossy environment. So based on this motivation, let's look at the years of research in delay-tolerant networking. We know that the host-centric IP architecture was designed for point-to-point communication. And this works well in stable infrastructure settings. But DTN changes this basic assumption. That is why people have been looking for different approaches, such as based on a data-centric design concept. For example, using unique identifiers for each piece of data, such as the epidemic routing protocol, and also securing data objects directly, such as the bundle protocol and the bundle security protocol. So these are just some examples of research efforts in this direction. Named data networking, or NDN, is a new network architecture which by nature supports delay-tolerant net communications, and it also supports many other network scenarios. So in NDN, each data has its own identity, independent from the containers. So a requester can fetch data from anywhere in the network based on its unique name. So if you look at the data packet format on the right bottom corner, you'll see that each data name is bound to its content by a signature. This signature is generated by the data producer when it first produced this piece of data. And starting from the point when the data was produced until when the consumer fetches it, the data itself can be authenticated anywhere in the network. So the main idea of this paper is to compare the data-centric solutions over existing IP architecture. So in this paper, we used epidemic routing as an example, and we want to compare it against NDN's data-centric transport, DDSN, which stands for distributed data synchronization over NDN. So the underlying architecture difference causes like a variance in design performance as well. For example, epidemic routing, which we will just call ER for short, does not consider security in its design. And the existing channel-based security model of IP does not work for ER either under delay-tolerant environment. On the other hand, DDSN is built over NDN, which has end-to-end security built in, as we mentioned earlier. So by comparing the differences and similarities between these two solutions, we try to find the design variations which causes the difference in protocol performance. And then we try to summarize what are the secret sauce to building a secure, efficient, and resilient communication protocol in DTN. So now let's take a look at the basic process for data distribution in ad hoc scenario. So first, as nodes move around, they need to discover their neighbors upon encounter. And then they need to exchange state information. So by state, here we refer to information about what data a node is holding. For example, A and B here is just asking each other, it's just telling each other, here's what data I have, and they're just transmitting their own state information. And then later, based on this state, A and B would fetch the missing data from the other node. So this is the data exchange process. Let's first take a look at epidemic routing. For data naming and state encoding, so ER runs over IP, which names nodes, and it also adds additional patch to name data. So ER adds a data identifier, which basically is a unique ID for each piece of data. And this is added in between the application layer and the IP layer. So the identifier is just a concatenation of the host ID plus a unique message ID without any semantic meanings. The neighbor nodes thus can identify missing data from each other through the exchange of what we call summary vector, which is encoding to contain a list of the data identifiers. And in contrast, DDSN also has data naming and state encoding. So because NDN directly uses application layer names as a network layer to communicate, this removes the semantic gap between the different layers, such as the application and the network. And NDN Sync adopts a structured namespace for the shared data set, as you can see on the right. So it uses a monotonically increasing sequence number to name data. And each data generated by the single producer will share the common producer prefix. So in order to identify what is all the data generated by the single producer, all you need to do is list that unique producer prefix plus the latest sequence number generated by that producer. And this two-value pair is encoded in what we call a state vector. So in this example, there are three producers, A, B, and C, and the latest sequence number generated by them are the following numbers in the state vector. The state vector here provides a compact encoding of state information, and its size only depends on the number of producers in the network. So now let's take a look at the data set state exchange process. So ER, or epidemic routing, is based on IP's node-centric communication model. So two nodes exchange their summary vectors using unicast communication over a broadcast medium. So this means if we have three nodes in the example, A, B, and C need to exchange state information with each other node, resulting in a total of at least 6 message exchanges. And DDSN, on the other hand, sends a sync interest containing the sender state vector in its name, indicating what data it has, and the packet is not sent to a specific destination. So any receiver can interpret the state vector from the packet name. And this fully utilizes the wireless broadcast communication model, as a single packet can be utilized by multiple parties. So, this is a basic experimental setup we had. So basically, we used 30 mobile nodes in an 800-800 grid, and we adopted the random walk mobility model. So let's take a look at the data retrieval delay. So on the left is the data retrieval delay for epidemic routing under different loss rates. And on the right is the same result for DDSN. The y-axis is just a CDF plot. So by data retrieval delay, what we mean is the total number of time it takes for all the generated data to be received by each individual node in the network. And the unit is in seconds. So DDSN overall shows about 34 to 70% lower data retrieval delay compared to epidemic routing under varying loss rates. So this is mainly due to a few reasons. First is host-centric versus data-centric state exchange. So for epidemic routing, nodes only exchange state when it encounters a new neighbor. And this is based on its node-centric design because the beacon message for neighbor discovery only contains the node identifier. But for DDSN, nodes exchange state upon encounter. And whenever a new state information is detected, it is immediately propagated to the rest of the network, minimizing the delay in state update. So the second difference is the point-to-point versus multi-party communication, as we mentioned earlier. So wireless network is broadcast by nature. However, ER is designed on top of the point-to-point communication model of IP architecture. So it doesn't really fully utilize this broadcast communication channel. And this will result in the variance in data retrieval delay. So another reason we want to analyze is the resilience to loss. We can see here that under different loss rates, DDSN has much more stable performance compared to ER, as the different color lines in figure B are much more closely aligned together. So this is due to several reasons. First is the data-centric state propagation, which allows lost updates to be retransmitted whenever state difference is detected. And the second reason is the periodic state synchronization of DDSN. So this allows the node to periodically detect state mismatch in the neighborhood, and this provides a faster detection of data loss. The third reason is DDSN node maintains a local state of what data it is missing. And this local state allows each node to fetch data persistently until all the missing data are retrieved. And ER, on the other hand, relies on peer encounters to actually exchange state information, then initiate the data exchange process. So the state and data exchange processes are bundled together. For DDSN, state and data exchange are separate. You first exchange state, you maintain a local state, and then you fetch missing data periodically based on this state. Now let's take a look at the overhead performance. Overall, DDSN generates about 40 to 45 lower overhead compared to ER. By overhead here, we just mean the total size of all the packets transmitted in the data distribution process. So the main contributing factor is due to the difference in state encoding. For example, shown on the bottom here, for summary vector, it enumerates all the UIDs of all the packets a node carries, and its size scales with the total number of packets generated. But for state vector, due to the structure namespace, its size is only dependent on the number of producers in the communication group. So even though if you have two producers, even if they generated like a huge amount of data, you only need to have two entries in the state vector, which is the producer name, prefix, plus the latest sequence number. Now let's summarize the lessons we have learned in this paper. So first, for delay-tolerant communication, we know there's a need to name data instead of nodes, and security plays a vital role in ad hoc communications. Second, for epidemic routing, it basically patches data identification and caching into the IP delivery model. And it cannot make use of existing IP-based security due to the lack of a stable communication channel. And due to data encoding, it is very tedious to exchange state information during ad hoc encounters. And third, for NDN, which names and secures data in the narrow waist, all NDN nodes can act as data mules. And the structure namespace of NDN leads to very efficient data state exchange and very compact data encoding. So this is the end of my presentation, and thank you very much for listening.